In the last lesson, we defined what a scalar and a vector is, and also provided a couple of examples. But we didn't show how a combination of these vectors sum together. We also didn't show what it really means to sum vectors together, and also why it's useful to do in physics. So we're going to cover that in this lesson. So in physics, vectors act on objects. In other words, objects are influenced by a quantity that has both a magnitude and a direction of motion. So our vector A here has a direction in the positive x direction, and its magnitude is represented by the size of the arrow here. So the vector A here that's acting on our object could be a force. And when a force acts on an object, this object will accelerate because force is proportional to acceleration. But this vector A could also be a displacement vector. In other words, it will be giving us a description of the direction that this object is traveling in and how far it's gone over a certain time period. If we have a look at an everyday example, say this rectangle here represents a car, and we have a vector that describes a velocity in meters per second. Our velocity vector acting on our car allows us to know how the car is going to behave in this given instant. But if we have two vectors, what does it mean to say they're equal to one another? Let's say we have two cars now, each being acted upon by its own velocity vector. If these cars are moving in the exact same direction, for example in the positive x direction here, and at exactly the same speed, in other words the arrows or the lengths of the arrows are exactly the same, then their velocities are also identical. And if we rename our velocity vectors here, so the vector working on car 1 we'll call A, and the vector working on car 2 we'll call B. If these velocity vectors are identical, as they are here, then A is going to equal B. If, say, the A vector either grows in size or shrinks down, or changes direction, so if it's pointing, say, in the positive y direction instead, then these velocity vectors are no longer equal. And it also doesn't matter where these cars are in relation to one another. If their velocity vectors are pointing in the same direction and have the same magnitude, then they're identical. Let's imagine we have a single car now, and your car's broken down. If you and your friend push the car from behind, both of you are pushing in the same direction and with the same intensity. Therefore, both you and your friend's force vector, so these are force vectors now, would be both identical. So A will equal B, because they're pointing in the same direction and they have the same size. But now the car's force vector would be the sum of these two vectors here. So the car's vector will equal the vector A plus the vector B. And we can draw this geometrically by joining the tail of one vector to the tip of the other. So if we start off with A, we can add B onto this vector, and the resultant vector, C here, is the sum of both vectors. And as you can see, it's pointing in the same direction. And it's important to stress here, whenever we compare or add two or more vectors together, they must have the same units. Because if you use different units for these vectors, their magnitudes won't add up properly. And they also must have the same type as well. So you can't add a force vector with a velocity vector, because these two vectors describe totally different physical quantities. Another point to mention is the magnitude of a vector, which we can represent like this, for example, can never be negative. It's always above or equal to 0. Now, vectors themselves can be negative. So, for example, this is allowed. But the size of our vector will range between 0 and upwards towards the limits that nature allows. And this will depend on the type of vector we're talking about. So, for example, if we're looking at a velocity vector's magnitude cannot be above the speed of light. But a displacement vector could have the size of the observable universe. Now, what we've done here is we've added two vectors together that are pointing in the same direction. But quite often, we'll have a situation where we have multiple vectors, more than two, that are pointing in many different directions. Now, how do we add all these vectors together? So let's take another example that also works with force vectors. So imagine you're a mother or father in the middle of a shopping centre, and you have 4 kids pulling at you in 4 different directions. And the kids here are represented by these red circles here. Each of these 4 kids will have different force vectors with different magnitudes, so different lengths here, and will be pointing in different directions because they want to go to different stores. When all 4 of these kids pull at you at the same time, we can add their force vectors together and find the resultant vector acting on you. In effect, we're discovering which direction you're going to be pulled in and how strongly. If we take all our vectors now and join them together, making sure that their lengths and directions stay exactly the same, our resultant vector can be drawn from the tail of the first vector to the tip of the last vector. And this will show you which direction you'll be pulled in. So in this case, you'll be pulled in this direction. So roughly that direction. But if we want to know exactly what the resultant force is, and the angle in the xy plane, so for example, what this angle is that we're going to be pulled in, and the length of this resultant vector, or the magnitude of this resultant vector, we would need to separate each vector, each of these vectors here, A, B, C and D, into its xy component vectors, and then use trigonometry to add all these vectors together. So for example, if I take A, vector A, it's pointing in this direction. Say this angle here is 40 degrees, and its magnitude is 30 newtons. We can break up this vector into its x component, which is equal to 30 cosine 40 degrees, and also its y component, so this component here, which is 30 sine 40. And this trigonometric analysis will allow us to extend easily into 3 dimensions, which this geometric method doesn't allow us to do. And it's more accurate as well. But I'll cover that properly in the next lesson. But what we can actually do when we break up each of these vectors into its x and y components, we can add these x and y components together for every single vector and obtain the x and y components for the resultant vector. If we've got the x and y components for the resultant vector, we can find out the angle of the vector in relation to the x-axis and its size using Pythagoras' theorem. So if the y component here, and the x component is the sum of all the x and y components of these vectors, we can find r using this equation here. And the angle would equal this. But I'll discuss this in far more depth in the next lesson. So just a couple more bits before we end this lesson. With this shopping centre example, it doesn't matter which order we add these vectors together. We could start with C and then B, A and D. We'll still end up with the same resultant vector, with the same size and the same direction. And this is because the kids haven't changed their direction or the strength they're pulling the parent. Algebraically, this is known as the commutative law of addition. In other words, if you have just two vectors, A and B, this would be identical to B plus A. It doesn't matter which way round you add the vectors together to get the resultant vector. And we can actually see this geometrically by taking apart our vector diagram here and adding the vectors in a different order. We will still have this resultant vector here, at this angle, at this distance. And here you've got the resultant vector pointing from the start to the tip of the final vector, and it's the same direction and the same length. And finally, I want to talk about what a negative vector is. So a negative vector has the same magnitude of its equivalent positive vector. So let's say A is our positive vector here, going in the positive x direction with a magnitude of, say, 100 newtons. But the negative vector would be equivalent to the positive vector, but pointing in the opposite direction. So it would have the same magnitude, but a negative sign. And also notice here that the magnitude, the value of the magnitude is a positive number, because the magnitude can never be negative. So think about the game tug of war, where two teams are pulling on a rope in opposite directions. If Team A exerts a force vector in the positive x direction, and Team B exerts a force vector in the opposite direction, but with equal magnitude. In other words, the force vectors are exactly the same, but in different directions, in opposite directions. Then the forces cancel out, and you result with a force that equals 0 newtons. In other words, say Team A has a force vector of positive A, but Team B has a force vector of negative A, then these two vectors cancel out because they have the same magnitude but opposite directions. So in the next lesson, we'll look at how to add vectors more precisely than we've done in this lesson. And we'll do this by breaking up the vectors into its x and y components and using trigonometry.